So today we're going to go over a little bit of chapter 11's teaching tutorial. And this teaching tutorial is going to do some extra raster stuff. So last time we did some basic introduction to what rasters are and how we can analyze them, specifically with the digital elevation model. We're going to be taking it up to a little bit of a next level here with chapter 11's tutorial. So I've opened the map, the raster analysis map for this chapter, following this step right here. Remember to save often. And then one of the first steps they want us to do is to click on analysis and click on environments, geoprocessing environments. Let's just make sure we're there. Yeah. This is something that already existed, so we open it up right here. So class project, so under the data folder for this book, class projects, raster analysis, and then there's a APRX file in there. That's just called raster analysis. So that's what I've opened up. So here's the geoprocessing little box under analysis and then environments. And then it says, note the current and Scratch workspace are set to the home geodatabase. You can change these if you want to have Scratch. Just means like when you're doing a bunch of different intermediate steps, where do you want that to go? You could just create a new Scratch geodatabase. And so I just right clicked and I could do file geodatabase and create a new one just called Scratch right here if I wanted to. Of course, that's going to take a minute. For something like this, we don't actually need to do that, but for a project that you're going to be working on over many months, you don't want to clog your geodatabase up with a bunch of garbage that you don't care about. So that's Scratch. Set the processing extent. So extent setting to same as layer. Let's look at that real quick. Processing extent. And then under same as layer, we're going to click elevation. And what that means is whenever we do some kind of clipping or projection or whatever with a raster, we're going to keep that within the same extent as the original raster. So as we create new products, it's going to follow the same extent as the original raster. And so this grabs the coordinates from that raster that bounds it. Snap raster. Let's see here. Processing extent. Set the processing to snap raster to. Okay, so raster analysis, snap raster, elevation. Snapping your raster means how do the cells line up? When you reprocess something, the cells could be shifted over here or a little bit offset. Snapping means that the cells are always going to be right on top of each other. And that's really important for a lot of reasons. We'll find out when we do the digital elevation model differencing. You want your cells to line right up, especially when you do like Raster Calculator. When you do something plus another something, everything has to be right on top of each other to work well. So that snaps, and this sets the elevation raster to be everything snaps to that base raster. Okay, change the raster analysis cell size setting, cell alignments. That's the snap raster is already doing that. And then cell size setting, where is that? Here we go. Cell size setting, same as layer elevation. So now the cell sizes, they're going to be snapped and they're going to be the same size as elevation. And I think that's going to be it for now. I'm going to click OK. So if you set that up front, then everything you do is going to kind of be nicely aligned and work well. And you don't have to kind of forget, oh, I forgot to snap the raster. It's always going to do that. So I save that, and that saves those settings. Let's go down to step 14. Hopefully we can kind of pick up from here. And we're going to do some distance functions and buffers. So vector analysis uses buffers to evaluate the proximity to a feature, 200 meters from a road, for example. We can do distance analysis in rasters, which can be much more powerful and flexible because rasters can store continuous distance information. So a buffer is just, are you in or out, 200 meters or not, right? But rasters can say, are you 100 meters, 151 meters, right? You can have that gradual distance away. So that's that continuous distance information. So vectors are discrete, yes or no, in or out, and rasters can be continuous. All right, so let's go and turn all the layers off except for roads. And we're going to use we're going to actually create a distance raster. So let's find Euclidean distance. And actually, before we start, let's just double check the coordinates of our raster coordinate system. Spatial reference. Okay, so it's UTM 13N meters. All right, so that's good. We have a projected coordinate system. That's really important when we're doing raster analyses, that we have our raster in XY units rather than lat long units. So projected coordinate system rather than a geographic coordinate system. So Euclidean. Okay, input raster or feature data source. So we're putting in a feature data source, so the road network. And then it's going to create a raster for us. We'll call that road distance. Output cell size. Looks like it's got some kind of raster in there already. So you could choose the cell size to be what the existing information is, or sorry, the existing raster is, so it kind of matches, right? This particular raster right here that's entitled elevation is actually called topo 30 meters in that Geodatabase. So they just renamed it. So that's why it says topo 30 meters right there. We'll keep that because we want it to be 30 meters. And then the distance is planar. The other options here are geodesic. Geodesic deals with 3D coordinates, right? Lat and long. But we're going to do planar because we have a planar coordinate system, right? That projected coordinate system. So let's go ahead and run that. Output direction raster. Let's take a look at that. The direction raster contains the direction in degrees that each cell center is from the closest source cell center. Does that make sense? So if I did a direction raster and I clicked on it, instead of giving me distance, it would say what direction, basically like a compass, that where all the roads are magnetic north. So based on the closest road, what direction am I to that road? Does that make sense? We'll do a direction raster when we deal with raster hydrology, because you want to know which way it points downhill. Oh, it did say to do it? Okay. Thanks, guys. Okay. Road direction. And we'll just call this one road distance 1. Whoa, look at that. Yeah, careful what you're on when you look at this stuff. So here's the direction raster, and it compartmentalized it. So if I click on one of these cells, let's see what it tells me. It gives me the actual degree, so 322, but this is gradations basically. So they just grouped it. They said north is 0 to 22 degrees. But really there's a continuous, or I guess maybe integer raster underneath here. So we'll deselect that one, look at our road distance, and this kind of makes sense, right? We're close to roads is green, farther away from roads is yellow. Okay, so we turn off the road direction raster, open the symbology pane for distance, and change the method to Jenks. So I'm going to double click on that color. And right now it's stretching. But I think we need to, let's see here. I think we need to go to classify and then Jenks. Normally, equal interval is appropriate classification for distance rasters, but in this case, the roadless area in the upper right is skewing the measurements in the symbology. So that's why we're doing Jenks. Jenks finds kind of natural breaks in the data. So if we were to do, let's just look at that equal interval, then basically what happens is everything washes out. You can't see any difference here because there's not a huge difference, right? 0 to 2,000 feet or meters, I guess. And up here, it's really, really far away. So we don't get to see anything interesting happening here. So we want some kind of different scheme. And that could be quantiles. Quantiles finds equal amounts of observations and splits it up that way. That's a little too dramatic. So Jenks is just kind of a little more intuitive type of classification. So let's just click on a value and see what we get. 1281, that's going to be meters. The closer I get to a road, the smaller the value is. And then we'll go look at the road direction, very trippy. And it bins up these values for us. So actually north, it gets both sides of the compass. So 0 to 22.5 and then 337 to 360, right? So it's got this little pi wedge that's centered on 0. In chapter 9, we introduced buffers. We can use Raster Calculator to do a buffer in rasters, where it's basically a buffer is 1 for inside the buffer and 0 for outside the buffer. So let's do that for 300 meters, and we'll open the Raster Calculator. I'm going to turn off the direction and turn back on our road distance. And note that we created this raster out of nothing, right? It was just, we didn't start with a digital elevation model or anything. We just said, give us a raster where every cell is so many meters away, right? It has a value of so many meters away from a road. And because we set the environment up to match this elevation raster, it spit out a raster that has the same footprint, right, as that elevation raster. And if we zoom in, we'll note that the cells should line up exactly with the elevation raster cells. So you can kind of point your finger on the screen and you'll see that those cells lined up. So 30-meter cells and 30-meter cells. That's important if we're going to combine the elevation raster with these other rasters. So Raster Calculator. And this is the expression we're going to enter. I'm just going to type it out. So here are the variables we can use, the rasters we can use. So road distance, I double click on that and it pops it in there. And we're going to say, you could also type it, but you have to use a certain kind of grammar basically to get it to work. So you can't just type road distance, it has to be in quotation marks. So road distance less than or equal to 300. It doesn't know the units. So the 300 has to be tied to the units of the raster, which we know is meters. This less than or equal to is a single operator. We can scroll down and find it here, less than or equal to, but you can just type it in, that's fine. And then we're gonna name it. And when you click on that, it gives you the full path. Because you've already set the directory to be that geodatabase, you can just type the name in. So I'm going to just do road buff 300. You can get a little bit messed up if you delete like a / or backslash, right? So sometimes it's easier just to do this. Go ahead and run that. And there's our raster, our calculator. So it gave us a 0 value for everything outside of that buffer and a 1 value for everything inside that buffer. There's a way to do it so that you get no data, where 0 would just be no data and be blank. And that is, you have to get into some if statements and that sort of thing. It's a little more complicated. We can also create multiple ring buffers with rasters. An example to consider is snail habitats. Snails tend to get crushed on roads. That's very sad. So the best habitat is far away from roads. Snails rarely travel more than 400 meters, according to biologists. So their whole life, yeah. Put little GPS tags on a snail and kind of watch it go. I mean, 400 meters for a snail? No, it's just turbo.
Yeah, but there's just so much to the world.
Yeah. Okay, so now what we're going to do is create 200 ring buffers using the road distance tool. So let's go ahead and do reclassify. This is a really good one. I like reclassify. And so when you see this tool reclassify, there's two tools. They basically do the same thing. I don't know why one's, so one's in the spatial analyst package or extension, and one's in 3D analyst. You can see how these are the extensions that we had to activate, and there's a special license for it. Through CMU, we get all the licenses for all the extensions. For a private company, they have to pay extra for these. And so that's just something hopefully they've done and that it's been activated. So just something to know. When I worked at a consulting firm, I'd turn ArcGIS on and then I'd have to check out the extension library from the server, right? And it took a minute to do. It was a real pain in the butt. And the company had like 20 licenses, right? So over the whole country it was a national firm, we had like, so many licenses to check out. But that's just something to point out. So we'll click on reclassify. I'm just going to see if it is different between spatial and 3D. Kind of looks the same. There might be some differences there. Let's bring in our road distance raster. We're going to reclassify the value. That's just the value of the raster. So let's just bring that road distance back up. And what we're going to do is what the way reclass works is it takes, and it does this for you automatically. You get to choose how you want to do it. What it takes is, okay, here are all the values, 0 all the way to 9,379, right? And it says, we're going to reclassify those into something else. So right now it says 0 to 662 is going to be 1. 662 to 2022 is going to be 2. And that would just change the values of the raster to these new things. You can kind of think of it as contouring. If the road distance, you're basically making contours in the raster, but you could change it to any values that you wanted to. We want to have 4 classes. And we're going to just do manual intervals. Let's see, you have to play around with this sometimes. So 4 classes. So I clicked on that classify button, I got to this. And then it says classify it this way. So we can actually go in here and let's just make sure. I'm going to go to manual. I'm going to press OK. So now we have 4 classes, and then now we can just change this as we want to. So 0 to 200 is going to be 1. 200 to 400 is going to be 2. 400 to 600 is going to be 3. 600, and it figures out how to, it's going to do 600.000001, right? To 9,400, it's going to be 4. And then no data is going to be no data. And then we're going to call that ring buff 200. And then it says change missing values to no data. If you have a gap in here, I think it's probably going to figure out how to lump it. But you could also say, if I have some gaps in these ranges, then just change the missing values to no data. Well, we're not going to check that though. Let's go ahead and run that. Now we've got this funky ring buffer. And you remember when we're looking at the digital elevation model, we had we use kind of discrete colors or unique colors. That's where you can go and do that for here. So let's look at symbology again. I'll double click on that. Here's the current color scheme. I don't really like that one. Let's do a gradation one. That's kind of random colors. Let's find one that is a little better. Got to find a good color scheme, right? All right, we'll just stick with that. That looks good. All right. So that's our new color scheme. Now we're going to do one more analysis here, or I guess a couple more analysis here, but we're going to bring. We've got this kind of weighted raster. So 1 is really close to the road, 4 is really far away from the road. And it took that continuous data and kind of made it a little more simplistic. We know that sweet spot is at least 400 meters for our snails. So we're going to create a new raster. Let's see here. We're going to multiply the ring buffer with the snail habitat raster. And maybe this is where we created a habitat raster from before. Hang on here. So I'm just going to keep talking to myself here. The next step is bringing in snail habitat, which was calculated in previous steps. So I've provided that to you. The way this was calculated was bringing in vegetation density, which was generated from a shapefile, a raster generated from a shapefile, elevation range, as well as underlying geology. So those were 3 rasters that were created as 1-0 rasters. One where there was appropriate geology, vegetation density, or elevation range, and 0 everywhere else. And then this snail habitat raster was created by multiplying them together. So density of trees, limestone, and elevation range. These were all, wherever it was 1, we got these colors basically. So this is where everything overlapped and created appropriate habitat for the snails. Everything else is 0. So that's why I have it as 1 is blue and then 0 is no color. So the next step is to then multiply this by our ring buffer that we previously created. And so we'll do that again in Raster Calculator. Go ahead and save this. Here's our snail habitat. We'll do times our ring buffer, which was right here. And the ring buffer is starts at 1 and goes for at least, I think, 200 meters, and then 2 for 400 meters, 3 and 4 for further. And we'll call that distance habitat. So now we have this raster that I'll give 0 no color. We have this raster that tells us with the existing snail habitat, how far away from roads are we? Because we don't want the little snails to get crushed. And let's go change these colors to kind of help us visualize it a little bit better. We're going to do red, orange, yellow, and green. So red, orange, yellow, and green. So these little yellow and green zones, we can say, are kind of the special spots for our snails. There's very little habitat that's safe, right? There's a lot of roads nearby, so these poor snails. So the distance raster was really important to kind of identify how the roads interacted with the actual snail habitat. Yeah. Now we're going to, now that we've created the snail habitat with distance on it, we're going to compare a couple other things. So it says compare the rasters of the ring buffer 200, ring buffer 300, which was just a 0 and 1, and the road distance layer. So we're going to take this habitat off and put our road distance. Oh, that's road direction. Here's our road distance. So road distance has continuous values. Our road buffer is 0 and 1. So let's just do that. Here we go. Continuous values all the way. So each cell has the distance away from the road. The road buffer 300 was just, are we 300 feet or not? Let's look at that. So are you in or out? And we'll make that a no color value for out. So in or out for the road buffer. And then this actually gave us graded values. So we started with the road distance and reclassified based on intervals of 200 meters. We're going to do one more thing, and we're going to open that Euclidean Distance tool again. And Euclidean is distance in the X and Y plane, planar distances. And let's go back to our roads. So put our roads features in, I'll bring that back in here. And we're going to do an output of minimum distance. We're going to call that min distance. And then we're going to say 300. So that's going to be basically just a 300-meter buffer. We don't need the direction raster, and we'll go ahead and run that. All right, so we'll turn off all the layers except our min distance and our buffer 300. And we'll compare these. So the min distance, it said, give us the distance up to 300 meters away from a road and give us a raster for that, but stop at 300 meters. And then the buffer 300 just said, give us 0 if you're within 300 meters and, or sorry, if you're outside of 300 meters and 1 if you're within 300 meters. So they share the same footprint, but in this case, it's just 0 or 1. And in the case of the distance raster, it tells us the actual distance. So that's just a comparison to do. It does look like a buffer, but in fact, it has those continuous values. And we call the 0, 1 buffer, the 0, 1 raster, a Boolean raster, because it's 0 if it's false outside of 300 meters and 1 if it's within 300 meters. I'll stop there for this video. I'll have you do the topographic functions to step 29, and then we will continue on from 42 to 51, which is going to be an analysis. Let's go down to 42, where we'll do interpolation and zonal statistics with rasters. That's some good functions to use as well.